Hello everyone, welcome to a new video in algorithms and constructs, and in this opportunity we're going to continue the previous class on mapping and hashing. Now we left the previous class when we talked about having a hash table with two values colliding into the same cell. So what happens if we have that situation, and how we can solve this situation, how we can deal with the collision of these two elements into the same cell. But there are different couple of ways, but the easiest one would be what is called the linear probing. So linear probing is once you have one cell that is already been taken, then you try and probe the following cell. So suppose you have an element that is mapping to index 4. If that index is already taken, so then you go to index 5. And if that is taken, you go to index 6, and so on until you find the index that is empty. So let's get back, for example, to the original to the example that we did before. So I'm assuming that each letter of the alphabet has a value starting at A with value 1, B value 2, C value 3, and so on. So when I'm going to map the word cat, for example, cat would be 24, and when I'm going to use the compress function to move 24 into the array, so my compress function is going to put cat, ear, aid, and sad, all of them in position 4, because all of them are 24. So in that situation, the first one that comes in goes to position 4. That's fine because it was empty. But then when ear comes into play, he finds the position 4 is taken, so he has to move to 5. Then then sad comes in, and cat is taken, ear is taken, so sad has to be stored, and finally aid has to go position 4, 5, 6 until he finds an empty position at 7. So the problem with this, well, this approach is complicated several ways, but starting, the first problem would be that now the element is not at the position that the hash table is saying. So that means that my complexity is not O1 anymore, because now I have to start probing. And in this particular case, I'm probing linearly. So that means that I need to go one element after the other. So straight away, my complexity is growing a little bit. And the other problem that I have is clustering. Clustering would be a big chunk of elements that are all together, as opposed to having a nice even distribution of data in the array. So I have another example in here. In this case, my hash table has 13 spaces as opposed to 10. And my hash function is going to be the module 13. So that means that I need to divide x by 13. And then if I have any remainder, that remainder is going to be between 0 and 12. So if you insert, for example, the key 18, when you map 18, that will give you the remainder 5. So you would put that in that particular position. Then from 41 would be 2. For 22, it would be 9. For 44, it would be 6. And up to that point, that's fine. But then for 59, it's also going to be 6. So I need to move to the next position. So something that I would like you to do is to pause this video for a little while and try to do this mapping yourself, just to get the idea of how this mapping is done. So in more programming terms, if I'm going to implement a map myself, and I'm going to implement the put method using linear probing, well, there is a couple of things that my method has to do. It has to throw an exception if the table is full. It has to start at the cell of the hashing function, so start at the cell h of k, and then we start proving or probing consecutive cells until one of the following things occurs. So if the cell that I found is empty, I can store in that particular one, or and all of the cells have been probed and none of them is empty, in which the case in that case is that the table is full. Now, another concept that might be a little bit difficult to see at first is the idea of a defunct object. So the defunct object is going to be an object that we're going to use to replace elements that I have deleted from the map. And well, let's have a look at a couple of things in here in order to understand what this idea is. So suppose we're going to remove the element with the key k. So I apply my hash function to k. I find an index and I go to the index, I find the element, so I can't remove it. So instead of removing it, I'm going to replace it with the element defunct. So let's see why. So let's suppose this hash function that I have in here with this hash table. So I have 3 elements, x, y, and z, and they're all mapping to the same value 3. So when I insert x is going to be mapped to 3, that's fine. When I insert y, it's going to be mapped to 3, but then I'm going to find that 3 is already taken, so I need to move to the next position. And then when I insert z, also maps to 3, it needs to move to the next position and then needs to move again to the next position because they're all taken. Now, what happens when I remove? So if I remove x and just remove it, I'm going to have a problem because when I'm looking for y, I'm going to go when I'm looking for y, I'm going to go, I know y maps to 3, so I'm going to go to 3 looking for y. I'm going to find that 3 is empty, and I'm going to think, it's not here, so if it's not in 3, it's not anywhere. So I need to know that I need to have a way to identify that even though now 3 is empty, y might be somewhere there. So that's what the defunct element is going to be for. The defunct element is going to be a flag that will let me know currently there is nothing in position 3, but before there was something. So if you're looking for an element that it goes in here, there is a chance that is lower below. So if you go to an element and you find the defunct element, then you can move to the next one and look in case the one you're looking for is not in there. So if you have any question in this one, just let me know. Now, there are other ways of handling collision as well. There is something called the quadratic probing, which is pretty much applying a second hashing function, a second mathematical approach, or even simpler would be what is called chaining. So chaining would be, suppose you have 2 elements that are mapping to the same index. So instead of going to the next available cell, you can chain them just using a regular linked list. So the linked list that we implemented earlier in the semester can come very handy when you are chaining elements inside a map. That's something else that you can do. Now, the next thing is when we're implementing my hash map ourselves, we need to also implement the set interface. And why is that? Well, remember that the map is a set of key value pairs. So my set interface should be there and all of the rules that follow a set should be followed. So let's take a look at the interface of the set. So a set should have a method clear, a method contains, a method add, remove is empty, size, and iterator. So when I implement my own hash map or my hash set has to implement the set interface. So all those methods should be there. Now, at this point of the semester, we've implemented a couple of the data structures ourselves. But it's important that you are aware, and I'm sure you are, that the maps are already being implemented and they're built into Java ready to be used. So for example, the hash map class has all the interfaces, implement the interface of the map, and it has all the methods and implementations that you need in case you need to use them. So that's something we will use. The performance of hashing, it should always be O1. And in the case of searches, in the worst case scenario would be ON, depending if you have any collisions or if you have any clustering happening, the worst case would be ON. But definitely for inserting is always O1. Okay, guys, thank you very much for watching. I know this is a very dry class, but I hope everything was clear. If you have any questions, let me know in the live class. Thank you very much for watching again, and I'll see you in the next one.